In this video, we continue with Chapter 8, covering Section 8.5, all about Unitary and Hermitian matrices. In the first video, we're going to talk about the conjugate transpose of a matrix and Unitary matrices. And then in the second video, we'll talk about Hermitian matrices and their eigenvalues. So our learning objectives are to find the conjugate transpose, which is known as A star, of a complex matrix A, and determine whether matrix A is what's known as unitary. So let's talk about the conjugate transpose of a matrix. Problems involving diagonalization of complex matrices and the associated eigenvalue problems require these concepts known as Unitary and Hermitian matrices. You're also going to hear these concepts in physics class or in computer science class, and maybe even some physical chemistry applications. So that's why we're making sure to cover these topics in our linear algebra class, because you will see them in other non-math subjects. So it's important that you're familiar with the concept of a unitary matrix and a Hermitian matrix. So these matrices roughly correspond to orthogonal and symmetric real matrices. In order to define unitary and Hermitian matrices, you must first be familiar with the concept of the conjugate transpose of a complex matrix. So the conjugate transpose, we denote A with a star. Oops. I hit something wrong in here and accidentally had to refresh my little slide here. We just have to wait for the internet to catch up. So here's our conjugate transpose. So it's A star. Be careful, in SIMPy, A star does not correspond with the conjugate transpose. I'll show you how you can use the transpose function in the conjugate transpose to find this in SIMPy. So this A star, denoted by hand, is A conjugate transpose, where the entries of A conjugate, or A with a line over it, are the complex conjugates of the corresponding entries of A. And then note that if A is a matrix with real entries, then the conjugate transpose of A is just the transpose of A, because there is no conjugate part of real entries in a matrix. So to find the conjugate transpose of a matrix, first find the complex conjugate of each entry, and then transpose the matrix. So let's take a look at this example. So we're going to find A star for this matrix A here. So the entries of A, it's a 2 by 2 matrix, are 3 plus 7i, 0, 2i, and 4 minus i. So then we conjugate each one of these. 0, of course, is its own conjugate. So you can see 3 plus 7i becomes 3 minus 7i, 2i becomes negative 2i, and 4 minus I becomes 4 plus I. And then we just transpose that. So you can see the big difference here in the transpose is that the values on the diagonal flip, since this is an easy example with a 2 by 2 matrix. You can also do these calculations nicely in SIMPy. So what's important to know in SIMPy is you don't use a lowercase I for the imaginary number, you use an uppercase I. And then when I type 3 plus 7i, I do need to say 7 multiplied by I. So the star here in SIMPy is multiplication, the same with 2 multiplied by I. I often forget to do that, and I get the error message in SIMPy. So if you just type, 2i, SIMPy is going to give you an error, and it might take you a minute to figure out why. So remember to put the multiplication there. So matrix A, you can see is an exact match. And then to do the conjugate transpose in SIMPy, first you take the conjugate of matrix A, and then on the outside function, you take the transpose. Order matters, so we want conjugate to be the inside function and transpose to be the outside function. Otherwise, you'll end up with the conjugate of the transpose matrix. All right, so let's take a look at Theorem 8.8, some properties of the conjugate transpose. So if A and B are complex matrices and K is a complex number, then these properties below are true. So the conjugate transpose of the conjugate transpose just takes you back to A, because you're reversing all of your transposing and conjugates if you do those calculations twice in a row. A plus B conjugate transpose is A conjugate transpose plus B conjugate transpose. K constant multiplied by matrix A together conjugate transposed ends up being K conjugate multiplied by A transpose, A conjugate transpose. And then the product AB conjugate transpose is B conjugate transpose multiplied by A conjugate transpose. And that's because that's how the transpose property works for matrices. So the conjugate keeps that same order going. All right, so now let's talk about what it means to be a unitary matrix. So recall that a real matrix A is orthogonal when A inverse equals A transpose. In the complex system, matrices that have the property A inverse equals A conjugate transpose are called unitary. So a complex matrix is unitary when A inverse equals A conjugate transpose. So let's take a look at an example of a unitary matrix. So we are going to show that this matrix A is unitary. A is 1/2 multiplied by the 2 by 2 matrix, where you've got 1 plus I, 1 minus I, 1 minus I, and 1 plus I. So the way you check to see if a matrix is unitary is you multiply A by A conjugate transpose, and if that's the identity matrix, then that shows you that A conjugate transpose is the inverse for A. So you can see here as we work through the multiplication here, the 2 1/2s come out front, and we end up getting a quarter multiplied by 4004 as a 2 by 2 matrix, which just gives us I3, the identity matrix, I2, the identity matrix in 2 dimensions. And so we see, okay, A multiplied by A conjugate transpose is the identity matrix. So it follows that A is a unitary matrix because its conjugate transpose is also its inverse. So that brings us to theorem 8.9 about unitary matrices. So an n by n complex matrix A is unitary if and only if its row or column vectors form an orthonormal set in Cn. So we aren't going to prove this, but let's take a look at an example to see how it works. So we're going to show this matrix A here is unitary by showing that its set of row vectors forms an orthonormal set in C3. So A is a 3 by 3 matrix. And the first entries in the first row, we're going to call those R1 here. So it's 1/2, 1 plus I over 2, and negative 1/2. The second row is R2, and that's negative I over root 3, I over root 3, and 1 over root 3. And the third row, R3, is 5I over 2 root 15, 3 plus I over 2 root 15, and 4 plus 3I over 2 root 15. So the first thing that we have to do, because we're showing here, remember, that the column vectors form an orthonormal set in Cn, is to show that R1, R2, and R3 are unit vectors. And so we find norms of R1, R2, and R3, and you can check our calculations here. Each of those norms works out to be 1. And then the next step is to show that all the pairs of the distinct vectors are orthogonal. So we, using our definition of the Euclidean inner product, we're going to do R1.R2, R1.R3, and R2.R3. We're going to dot all these products, and we get 0 for all of these. You can pause and double check my calculations here. So because we showed that these are unit vectors and that all pairs of distinct vectors are orthogonal, R1, R2, R3 is an orthonormal set. All right, in the next video, we're going to take a look at Hermitian matrices and how to find their eigenvalues.